Okay, so our paper that we're presenting is the layer-wise relevance propagation overview paper.
Hey Nick, can you turn on the video? We can see.
Oh, yeah, that's right. Sorry, for some reason it turns off every time I take the screen over. Can you see it now?
Yeah.
Okay,
yeah,
cool.
That's good.
Great. So right, I'm Nick, and my partner is Surinder. So we can get started here. So just for this presentation, we'll go over sort of the introduction from the paper, which basically covers the background and motivation before we talk about LRP itself and the different LRP rules they discussed. And then we can talk about some guidelines for LRP rules for different layers in the network and move on to the conclusion and discussion. There's some more content in the paper about like LRP applications beyond deep networks, so we sort of trimmed down for time reasons. So maybe during the discussion, if we wanted to circle back to that through time, that could also be something we could do. So right, for the background and motivation, the first thing the authors talk about is they really attribute the success of machine learning techniques that we've seen in recent years to the rise of large data sets and our abilities to process them. But they mention that large data sets can be plagued by these spurious correlations, right? Like the correlations that the network picks up on might not necessarily indicate causal relationships, which leads to these clever Hans type predictors that we've been talking about. They give an example that I thought would be good to highlight here. So in this example, the real classification, like the actual class of circles and squares, is denoted by these ellipses here. And this model draws a boundary between them properly, but the other two models in this example still classify the data sets correctly with their decision boundaries, but they don't actually draw this boundary between the two real classes. So the authors say that even though all of these models are maybe making the correct predictions, only the first model generalizes to all cases, which brings us to the field of explainable machine learning. Sort of the first thing they touch on here is the idea of feature selection being one approach to this, which is where we only present the model with good input features. Then they immediately discuss some problems with feature selection. The first one is that it can be difficult to apply in practice if you consider like the amount of data that needs to be looked at and everything. And then they say, considering like image recognition, individual pixels don't necessarily have fixed roles, so it can be difficult to tell what might be a good feature from a bad feature as a human. And then they introduce the idea of explainable ML, which takes the opposite approach. So we train the model first, and then we look at which features the model actually learned. At this point, we don't care about feature selection because the bad features can be filtered out later, and then we can retrain the model on a sanitized data set. And one foundational XML topic that they discuss here, which will be used much later in the paper, is the idea of Taylor decomposition. So we'll take a look at that now. So the idea here for the simple Taylor decomposition technique is to produce an explanation by performing a Taylor expansion of the prediction function itself at some nearby reference point to the input. And then the first order terms, which are the elements of the sum here, can quantify the relevance of the input features forming the explanation. So this is a relatively straightforward technique here. And this is the reference point that we have to pick for the Taylor expansion. And then the authors immediately discuss some problems with Taylor decomposition. The first one is that it is unstable when applied to deep neural networks. They attribute this first to the shattered gradients problem, which is that while the function is generally accurate, the gradients are noisy. They contain very little meaningful information. And then they also give the example of adversarial examples, right? Small perturbations of the input causing dramatic changes to the function value. And there's also the problem of choosing a meaningful reference point, right? I mean, if you pick 0, for example, it might be far away from the real input. They briefly also discuss some alternative explanation techniques. They don't spend a whole lot of time on these, so we can just run through them quickly. The first is like the idea of integrating a large number of local gradients. Or replacing the gradient with a coarser estimate of effect, optimization techniques for like a surrogate model, or even for the explanation itself. But the problem that all of these share, that the authors are trying to sort of get around, is that they're all very computationally expensive. They involve multiple network evaluations, and we want something that is not so computationally expensive. This section here is the last thing from the motivation. It's not actually in this paper. I found it in a talk that one of the authors presents on the paper. So these are some other properties that they're trying to satisfy with their explanation techniques. The first one is the idea of conservation. So if we find explainable evidence in the output, it has to show up somewhere in the input. There can't be any loss of evidence. And this is a big one that they talk about through the paper and how this is actually enforced. The next one is the idea of positivity, which is that either a feature is relevant or it's not. Pretty straightforward. Continuity is the idea that if two inputs are almost the same and the prediction is almost the same, then the explanation should also be almost the same. And the last one is selectivity, which is the idea that models have to agree with the explanation. So for example, if we found some piece of evidence in an input image, and then maybe we blurred that section of the image, and then we refed the blurred image through the network, we should see a decrease in confidence in the output. And LRP as an explanation technique happens to satisfy all of these properties, whereas the previous ones and others don't. So that's an advantage of LRP. Which brings us to LRP itself, layer-wise relevance propagation. And this is an image, and we can sort of talk about it as we go through these points. The basic idea is that LRP as an explanation technique, and we talked a little bit about this, I think, last week in one of the papers too. So it's a backpropagation technique. We want to propagate the prediction backwards using some purposely designed local propagation rules, which we will talk about in the upcoming slides. And this is also subject to the conservation property. So whatever a neuron receives, it has to redistribute to the lower layers in an equal amount. It's also subject to the other properties, but this is the one that the authors explicitly mentioned. So really what we're trying to do here, if we look at the image in the top right, is we have this relevance score, RK, for this neuron, and we want to redistribute the relevance that this neuron has back to the neurons in the previous layer. So there can't be any loss of relevance going from the kth layer back to the jth layer, and then from the jth layer to its previous layer, and so on. So we really want a technique for propagating all of that information backwards without any loss. And then this, oh, sorry, let me hide that. This function here is the sort of general LRP rule that we're going to be expanding on moving forward. And that's basically how this propagation happens. We'll talk about the terms on this slide here. So referring to this equation, the Z quantity here, Z sub jk, is going to be the quantity that we use to model the extent to which a neuron J contributes to make the neuron K relevant. And then the denominator is the sum of all of these quantities from the J to the K layer. And we use that to enforce the conservation property. So the question here might be like, aren't we putting the cart before the horse a little bit, right? Like we want to determine relevance, but now we need to determine how are we actually going to get this this Z score, the contribution from some neuron J to the relevance of a neuron in the next layer. And the authors answer that question with the introduction of these different LRP rules. So I'll talk about three of them, which are the ones that the paper focused on: the basic rule, LRP0, and then the epsilon rule and the gamma rule. And an important thing to note here is that all of these are working within the context of ReLU activations. So this is the ReLU function that hopefully we're all pretty familiar with at this point. This doesn't really apply to any other activation functions. So talking about the basic rule, LRP0, the idea here is just to redistribute relevance in proportion to the contributions of each neuron, or of each input to the neuron's activation. So all we're doing for this is setting that Z equal to the activations times the weights, the input to the neuron. So this has some interesting properties. The first one is that if A, the activations or the weights are 0, then the relevance will be 0, which allows for compatibility with concepts such as zero weight, deactivation, things like that. And I think just intuitively that kind of makes sense, right? Like if either of these happens to be 0, then that particular neuron shouldn't really contribute much to the final output. We'll see a uniform application of this rule later on when I turn it over to Surinda for the actual image examples. But it winds up being equivalent to the gradient times the input, which is undesirable since, as we already mentioned, the gradients are typically very noisy. So this is the sort of general LRP equation that we had in the previous slide. And here, all we're doing to get the basic rule on the right is just substituting in the activations times the weights for this Z score. So now we can move on probably to the epsilon rule. So like we just mentioned, the basic rule itself happens to be pretty noisy when you apply it. So this rule aims to solve that problem by introducing a small positive term epsilon to the denominator. We're going to diminish the relevance scores here overall. And hopefully what we're going to do is absorb some relevance when contributions are weak or contradictory, things like that. So as epsilon becomes larger, because it's in the denominator, only the most salient explanation factors will be preserved. So the overall result is sparser explanations in terms of the input features and less noise. So here on the left, we have the basic equation we just looked at, where we have the activations times the weights. And the only new thing here is the introduction of this epsilon term. And like we said, the point of this is to sort of reduce the noise level. Another technique they talk about is the gamma rule. So the idea here is also to reduce noise and improve stability. But this time, we're going to favor the effects of positive contributions over negative ones. And we're going to do that with the introduction of the gamma parameter that we're going to apply to the weights, to the positive weights, rather. So as gamma increases, hopefully we'll see negative contributions disappear. And the idea is to limit how large positive and negative contributions can grow during propagation. So this is the basic rule again. And the new thing that we're doing here is, rather than just multiplying activations times weights, we're multiplying activations times the weights plus this gamma parameter that's applied only to the positive weights. So we want to amplify the positive ones. And we're doing that, of course, in the numerator and the denominator. As sort of a bonus, they talk very briefly about another rule that is sort of similar, the alpha beta rule. And like gamma, this one aims to treat positive and negative contributions asymmetrically, but it goes about it a little bit differently. This time we're applying two parameters, alpha and beta, to the positive and negative contributions. This is also subject to the conservation constraint, where alpha has to equal beta plus 1. And an interesting property they mention here is that in the LRP gamma rule, for the case where you set gamma to infinity, that causes the same behavior in the LRP gamma rule as the LRP alpha beta rule, where alpha equals 1 and beta equals 0. And this is from a table in the appendix for the alpha beta rule. So I guess the difference between the gamma rule is that instead of applying the parameter to the weights, we're applying it to the overall contribution here. Alpha for the positive and then subtracting beta applied to the negative. So that brings us to the next section, which is implementing LRP efficiently. This is the general LRP function that we're going to be working with going forward. So the only new thing here is the rho function. And what we're using rho for is basically to apply our LRP rule to the weights. Like, for example, if we wanted to use the gamma rule, then rho would take the weights as an input, and then it would return the weights with that gamma parameter applied to the positive weights as an output. If we were using the basic rule, gamma would just do nothing. It would leave the weights unchanged. And then the epsilon in the denominator, you could just negate that by setting it to 0. Okay, so considering this new generic LRP rule going forward, for any layer J, the relevance score can be computed in 4 steps. So the first one is going to be just to compute the denominator, and this is basically the sum of all of those contributions from the J layer neuron to the K. And then we're going to compute the relevance of the current neuron divided by those contributions. That's to enforce the conservation property. This third one is basically computing the numerator with the activations factored out times SK, which is the thing we just computed. So this is basically analogous to doing everything with the activations from the previous layer factored out. And then, of course, the next step is going to be to multiply those activations back in. The important thing to note here is that with this C, this equation here in the third step, we're assigning basically a value for how much relevance we want to propagate backwards to each individual neuron in the previous layer. And so what the authors mention is that we can actually think of this as being analogous to a gradient computation on the Z, this Z value, which if we think of Z as a function of the activations from the previous layer, and of course, remember Z is the total contributions from that layer, then we can get the individual contributions for each neuron by computing a gradient of that function. So this winds up being the same thing as this, and now we're able to think of it, since it's a gradient computation, as being a backward pass. The important thing to remember here too that the authors note is that here we have to treat S as a constant in order for this to produce the correct values. So now that we have this as a backward pass, we can think of like, PyTorch or other libraries that we might be familiar with. And if this first step is basically a forward pass and this third step is basically a backward pass, it should be very easy to implement. That's what the authors sort of show here. So this is the first step. And in PyTorch, that just basically looks like this. Add the epsilon to the row of the layer and perform a forward pass over the activations. The second step is very easy. We just divide the R, the relevance for the current neuron, by Z. They're just adding this small term to get around division by 0 cases. And then the third step, since we said this is analogous to a backward pass, we're just performing that backwards pass. And this is going to store the gradients in whatever we passed into the forward function. So then we're finally pulling those gradients out and storing them in C. And then finally, of course, we just have to multiply the activations times these contributions to get the final relevance for an individual neuron. So this winds up being a PyTorch implementation of the LRP technique. So the next section is relating LRP to deep Taylor decomposition. And what deep Taylor decomposition, which actually wasn't introduced in this paper, this was introduced in another paper that the authors wrote previously. So maybe there's some context that might have been helpful to know coming into this one, since this is more of a review of this technique. But basically what it does is it views LRP as a succession of Taylor expansions performed to each neuron. So we want to treat the relevance score as a function of lower level activations denoted by this vector A, and then perform a forced order Taylor expansion of the relevance score at some reference point in the space of activations. So the reference point will be this A tilde here. And then the first order terms, which is the sum, will wind up giving us the relevance that we can propagate backwards. So the authors mentioned that in order to actually compute these values, we need a closed form expression of the previous equation. So what we're going to do moving forward from this section is substitute that relevance function with a new relevance function. We'll call it r hat. That's easier to work with. And r hat basically looks like this. This is just the ReLU function. So what it takes is an input for a neuron times some C term. And the C is a modulation term. It's a constant. And we're going to set that constant such that r hat equals the actual relevance function that we've been looking at previously at the current data point. There is a proof in the appendix. It's very brief that basically says there is a constant that will do that. So this is okay to move forward with. And now the Taylor expansion becomes something very nice and in closed form that we can actually work with. So the next thing they do is they relate the different LRP rules to the deep Taylor decomposition and talk about how they can be recovered. So if you set the reference point to 0, you can recover the LRP0 rule. If you set the reference point to this expression right here, you can recover the epsilon rule. And then finally, if you set the reference point to this longer expression right here, you can recover the gamma rule. And we'll show this again on not this slide, but the next slide. So this was a diagram that the authors gave. I thought it was pretty straightforward to sort of follow. So now we're just computing the relevance for a neuron is the activations times this modulation term that we just introduced. We perform a Taylor expansion. So maybe here's the real activation, and then here's our reference point. And then the propagation works exactly the same way. It just flows backwards from the current neuron. And here, we're actually going to pull this apart in sort of the next slide. But this is just giving a sort of a 2D representation of this Taylor expansion and showing where in that space you could recover the different LRP rules. So this is just pulling one of those examples out. And basically, we're saying if we set the A tilde, the reference point, to 0, we can recover the behavior of the basic rule. And similarly, if we set it to this expression, we can recover the behavior of the epsilon rule. And finally, if we set it to this expression, we can recover the behavior of the gamma rule. And this would just show where in that space that would happen. Okay, so I'll turn it over to Surinder now for the different LRP rules for the different layers.
So I'm going to talk about which LRP rule for which layer. But first, we're going to talk about the properties of explanations. So LRP is a really flexible method because you can apply different rules for different layers of your model. And also we have the flexibility in setting epsilon and gamma for LRP epsilon and LRP gamma rules. But to actually optimize this flexibility, we need a quantitative measure of explanation quality, but that's still being researched right now, and we don't really have a definite way of quantifying that. So in its place, we're focusing on 2 qualitative explanation properties, which is understandability and fidelity. So understandability is very simple. It's simply how well we as humans can interpret a explanation. Fidelity is how accurate the explanation is to the representations of those neurons. But an important thing to note is these are qualitative measurements. So we're probably going to be measuring these visually. And if we're visually assessing fidelity, which is how accurate the explanation is to the model's workings, we're assuming that the model is solving the task that we gave it properly. So it's not having those clever Hans methods, because if a explanation doesn't look like it is representative of how we want the task to be solved, and the model is actually solving it that way, not how we intended it to, it would technically have fidelity. But for these cases, we're just assuming that the model is working as we want it to, and it is using the correct things in the image to create its classification. So in the next few slides, we're going to look at some examples of our different LRP rules applied to the VGG16 model. And this model is trained on ImageNet, the 1000 classifier dataset. And for these examples, we're going to be looking at the classification of this castle right here. So in this example, this explanation has the LRP0 rule applied to every layer of the model. And as Nick said earlier, it's essentially that gradient times, it just has that gradient times function appearance. And we have the red dots as positive relevance to the classification of a castle, and the blue is negative relevance. So this explanation is really complex, and it's very hard for us as humans to comprehend it. So it lacks understandability. Also, because the explanation fails to focus on the castle in the background, it also lacks fidelity. So in this explanation, we're applying the epsilon rule to all layers of the model. And the explanation is still really sparse and not very well outlined. So it still lacks understandability for humans. But because a lot of the noise is removed and it starts to focus in the general area of the castle, it has fidelity. And then finally, we have the LRP gamma rule applied to all layers of the model. And this explanation is very clearly outlined, and we can very easily understand the objects in the image that are being outlined, so it has understandability. Unfortunately, this explanation is outlining too much. So as you can see, this lamppost in the image is very clearly outlined in our explanation. And that makes it lack fidelity, because we don't want the model to be using that lamppost in this classification of the castle. So here we have an example of a compositive LRP. So here we have all the layers of the VGG16 model, starting from the input layer. We have our convolution and max pooling layers, and then finally we have our dense layers at the end. So for our upper layers, we're applying LRP0. For our middle layers, we're applying the LRP epsilon rule. And for the layers closer to the input, we're applying the gamma rule. And so as you can see, we have, again, a very well outlined explanation, especially for the castle. So this is a very understandable explanation. And because the castle is actually correctly identified, the lamppost is less outlined, and other areas such as this sign and this little bit of a roof in the corner are assigned negative relevance, we can definitely say that this explanation has fidelity. So now we're going to look at the rule choices that they have for each layer and why they assigned each layer the rule that it was given for VGG16. So again, starting with our upper layers, we have LRP0. And these upper layers, these upper dense layers, they only have about 4,000 neurons, which is 4 per class. And it's relatively less than the other layers in the model. And because of this, there's a lot of entanglement for concepts that the model is trying to assign to the classes that it's assigning to the input image. Because LRP is really close to the function in the gradient, it can ignore these entanglements when trying to visualize this process. For the middle layers, we have LRP epsilon rule, and the middle layers they're much higher neuron count, are much less entangled, but the layer stacking and convolution weight can add these spurious variations, as we mentioned earlier, those clever Hans behaviors. So with the LRP epsilon and that added in epsilon value in the calculation, we can filter out these spurious variations. And finally, for the lower layers of the model, we're using the gamma rule. And it is very similar to the middle rules, but using the LRP gamma rule at these layers can help uniformly distribute the relevance to whole features of the input instead of calculating separate values for each of the pixels from the input image. And this helps make the explanation much more understandable and much more well outlined to us when we see in the descriptions. And so here the authors are comparing two explanation metrics. So the first one is what was used in the earlier examples, and it is Z of C, for C being any class. And it is related to the actual prediction using a softmax function in this way. You simply pass it through the softmax function. And the explanation it's being compared to on the right is eta sub C. And eta sub C actually takes into the account of features increasing the probability of other classes other than the actual predicted class of the model. So in the Z sub C explanation here, where we're trying to classify this passenger car, the second car in the train, the entire train is actually given some positive relevance as they all do increase the probability of predicting that this image is a passenger car. But when we look at the eta sub C of the image on the right here, what this explanation reflects is that the inclusion of the first car in the train, the locomotive, will increase the chance that the model is predicting it as a locomotive. So while it still not be the highest class, that increase in another class is reflected in this model, and it's assigned a negative relevance. And correctly, we're mostly showing only red in the area of the actual passenger car that we're trying to classify. So moving on to our conclusion, LRP can help explain state-of-the-art predictions in terms of their input features by propagating the prediction backwards through the model by applying various rules to the different layers of a neural net. And these rules can be implemented very efficiently and modularly in most modern neural net softwares. Through parameter tuning, even the most complex models can have high-quality explanations. With neuralization propagation, or NEON, which was not mentioned earlier in the slides, but is in the paper still, LRP can be applied beyond just deep neural networks to other model types, and this increases its scope to explain problems that are still in machine learning, but not limited to being solved with neural nets. And for the four arguments for this paper, it satisfies the several properties of good explanatory machine learning techniques, as we said earlier with those four topics that only LRP satisfies. And it produces faithful and understandable explanations. It can be extended using NEON to a broad range of machine learning models, machine learning problems that we're solving beyond just neural networks. It can be implemented efficiently again compared to other explanation techniques. And it can be easily modified to fit a variety of use cases using the different rules for different layers in a model.
Yeah, and I can hop back on for the against points here. And I guess before reading over these, I should mention again that this paper didn't introduce LRP or deep Taylor decomposition. So maybe some of these critiques or criticisms might be addressed in the papers that did introduce those concepts. So like the first one, for example, there's little empirical evidence presented here. There's no real comparison to other state-of-the-art methods empirically. I'm not sure if maybe in other papers the authors wrote they covered that, but they didn't do it here. And then there were also like different LRP rules that were left out. They were sort of briefly mentioned in a table in the appendix, and it's really unclear why this is the case. are those rules maybe like less effective or less important than the ones that were covered here? Not totally clear. And of course, LRP itself only applies to ReLU activations, which is a very popular activation function, but there are others, right? Like the sigmoid, or like we talked about in the quiz. The explanation quality still requires human assessment. This is a big one here. That can be time consuming and error prone. I think there's a sub point on this bullet too. The next one then, yeah. So there's no formal evaluation criteria, only fidelity and understandability, which are subject to bias. And then speaking about fidelity specifically, this requires the assumption that the model is functioning the way we want it to. That was something that they mentioned when they were talking about these criteria. And then the last one is that the authors offer these different heuristics for applying LRP rules, such as like use the epsilon for middle layers, but they really only offer the support for these in the form of like intuition rather than like more rigorous forms of evidence. I think this is something we talked about during the discussion on Monday too, where it's like the goal of these explanations is to sort of give some more like reasoning behind like what the neural networks are doing exactly, but now we have these sort of heuristics for deriving the explanations, which seems a little bit to me like maybe, I don't know, it'd be nice to have something more formal or rigorous there. And sorry, this is the last one. The relationship to the deep Taylor decomposition framework is very clear, but what wasn't clear, at least to me in reading this paper, is why this relationship is valuable. Like, what do we actually gain from being able to tie LRP back to deep Taylor decomposition? And this might have been one of those things that was covered in an earlier paper the authors wrote. But the actual advantage of that relationship, I don't think they touched on really here in this one. And yeah, I guess we can open up the discussion now.